this class was written to kind of track my own journey from not knowing very much about electrical installation to becoming a solar installer. And eventually, I needed to become a licensed contractor, become an electrical contractor. And it turns out that in many states, if you're already an engineer and you pass the master electrician exam, then you can be a master electrician in that state. And so that can be useful for many reasons. As engineers, you're asked to be a project sign off. But that can also, particularly with the advent of solar and batteries, result in engineering managers managing electrical scope without having ever gone through a comprehensive introduction to National Electric Code. Now, that goal of covering all of electric code in 6 hours is not feasible. And so this class is a comprehensive introduction to code, a read through of code. But what we're going to do along the way is highlight or really just focus in on the aspects of code that have to do with on-site power generation and distribution, looking ahead to solar and batteries. So by the end of this class, tomorrow in part two, we're going to be talking about code specifically related to solar power and interconnection and batteries. But what I've found is if you just start with those special sections because you want to get a solar industry certificate and you want to know you're managing solar projects and you have to start somewhere, so you just start with, what do I need to know everything about solar? What you miss out on is an appreciation for the more general sections at the beginning of electric code, which govern basic things like conduit and cable and fuses and breakers. And it'll limit your solar design if you never go and revisit that initial generalized section of the beginning of code. And what you can also discover is if you have a solid appreciation for the general principles of National Electric Code, the specialty conditions you no longer need to memorize. You can say, okay, well, normally it would be this, but I know this special thing about this special device, and so I'm going to have to modify it from what's normal. You don't need to memorize all of code. Basically what code boils down to is a bare minimum safety measure. And so if you can reason through electrical safety, then that goes just hand in hand with National Electric Code. So one of the main things that we need as engineering managers or architects is to have our visions become reality. And solar costs have come down substantially over the last 10 years. There's other things involved, but to have our solar projects be stunning, to incorporate solar into the building and not just have it be up on the roof, to push the edge of solar design, you can't do that without a strong understanding of the fundamentals. Now, the National Electric Code is actually a private organization, and that makes it hard to teach a class on National Electric Code because we can't, give you a copy of code, and we are supposed to, have by reference only with code. So even in a code class, things like handouts and become a little complicated. So just know that the way code works is a private organization maintains it, and then local governments choose to adapt it or not. So there's certain states like Mississippi that aren't officially on National Electric Code, and then there's other states that require the latest and greatest National Electric Code. All right. there's no problem designing to the highest safety standard, where NEC 2020 is at. Code, most of the code is there for a reason. In fact, as we get to know code, we'll see that it's not rigid. It's a flexible tool. It's not trying to establish a maximum safety standard. It's really trying just to define what a minimum safety standard is. So let's start off with some 2020 changes. The first one, these are directly from the NFPA website. The first one is that code is consolidating to make it easier to find the information that you need. What we find is that code evolves. There used to be a small section on batteries, but now batteries are very different than they were just 10 years ago. And now there's a section on high voltage batteries that we'll get to tomorrow. So there are redundancies in code. You can be, if you just do a start to finish read through of code, you'll see the same phrases appear over and over again. You're like, I thought I just read that. And basically code repeats itself a lot, and then people get fed up with it, and then they try and do some consolidation. So that always occurs. This is the main one for NEC 2020 with regard to solar power, is the requirement for an exterior emergency disconnect at dwellings for emergency responders. And this has always been a debate about where the disconnect locations are on a solar job site. And it's had its ups and downs. A lot of utilities have stepped in and required these external disconnects. Independent, code just requires a disconnect. A breaker is a disconnect. So solar lands on a breaker, that's your accessible disconnect switch. Utilities have said, no, that's not good enough. We need a disconnect switch that's outside the house, and then often it turns into a knife switch. The code has now come down and said we have to have a switch on the side of the house that can de-energize the solar array during an intentional power outage. So if there's something going on in the building, the emergency responder can kill solar power, and that has to be outside the building. The main thing with these emergency disconnect switches is you need to lock them. And that becomes a logistical issue. Does the installer lock it? Then you give the keys and the lock to the homeowner because the installer doesn't want to ever come back on that job site when they're done with it. But if you don't lock your exterior disconnect switches, they become safety hazards themselves. People can open them up, stick their hand in, and electrocute themselves. So that's the main safety concern about these emergency exterior disconnects, is to make sure that they are locked up at the at commissioning, or when the grid side is tied into the top of that disconnect. Some other, there's expanded code on Ethernet cable. Another big one is updates for load calculations, namely with lighting load. So in code, there's parts where you can say, I need to plan for this many watts of power based on the building being for this use and this square footage. And those lighting loads were based off of incandescent light bulbs. Now we have LEDs, which are 80-90% more efficient, and so that's been updated. Introduction of requirements for the safe use of electric vehicles as backup or emergency power sources. I think that is a major step forward in National Electric Code. And what we see, just to kind of spoil the battery sections for tomorrow, is that they're breaking out code to say, okay, there's a difference between a manufacturer product like the Tesla Powerwall and a product that an installer assembles together out of a myriad of parts to have a code compliant system that way, but it's not a manufacturer all in one. So they're giving complete assembly, listed assemblies, more flexibility in design with harsher requirements for something that's been kind of tinkered together, which makes sense. But the big thing was that your batteries had to be listed for use. And so could electric vehicle, batteries intended for an electric vehicle actually be wired up to a home and used for home safety load? That is something that International Building Code has allowed, but not National Electric Code, which it took a more kind of murky response on it. So now we see kind of permissions to use electric vehicle batteries into the building starting to come into the building. So that's important because electric vehicles are the number one source of batteries, much more so than on-site storage, even though you could argue it would be better for the battery to stay in one place. And at any rate, the electric vehicle market's driving the battery market. And so what do you do when the batteries for cars have worn down to the point where they don't make a good car vehicle or they're getting swapped out? One answer is put them to use on a building. Is that allowed by code? Code's taking steps to say it's allowable. Okay, so we talked about how code is this kind of repeating pattern. The actual structure is we start off with definitions, very general stuff that you could read through and say, okay, I get most of that. Then we get into wiring and protection. This is one of the main sections of code for solar design. Wire ampacities, service entrance sizes, ground wire sizes, things that have to do with on-site power and distribution in general, show up in that section. After we introduce how power is brought into the building and distributed through through our electrical services, we're ready to better define the wires themselves. So after we talk about grounding and power distribution, then we get more into specific kinds of cables. What differentiates a indoor cable from an outdoor cable, temperature ratings, voltage ratings, and also the stuff that the cable goes into, metal conduit, versus a metal net, or outside a conduit, or plastic conduit versus metal conduit. So already we're seeing kind of a rhyme and reason to code. They start out very generally with fundamentals of electricity coming into the building. Then they talk about the wires, and then they talk about the equipment that it powers. So section 400 used to be kind of the equipment section, and then everything else is kind of tacked on to say, okay, well, there's some buildings are different than others, so there might be special rules for assembly buildings versus homes. And then we see this specialty equipment section towards the end that has defied the downward trend and instead is growing in size. What happens is there might be references to general equipment such as batteries that all of a sudden technology changes and they become more important, and so they add on special use cases. So a lot of solar battery stuff has their own section in section 600, but it might have some redundancy in section 400 as well. And then we get into 700, which governs batteries and interconnections. And then 800 is like Ethernet data cables. So thumbing through the code book, most of the time you're actually thumbing through the first half, and usually, in terms of cable sizing and ampacity and derating, that's going to be in section 200. But if it has to do with conduit or wiring, it'll go into section 300. Okay, let's talk about some, section 100, some definitions. Accessibility is capable of being reached for operation, renewable, and inspection. Readily accessible is even more accessible than that. So, if you can reach the disconnect, but you might have to have a step stool, that's an accessible disconnect. A disconnect that's, 6 feet up or 8 feet up the wall, where maybe you're stacking a whole bunch of equipment up a wall, and some of the inverters require accessible disconnect switches. You can't quite reach it, but you could with a stool. That's okay. Readily accessible is different. It's heightened. It says, without climbing or ladders. This was a term that threw me for a loop when I was looking for like special cases and exceptions. It'll say utilization equipment, can do this or that. Like, okay, so is utilization equipment utility equipment? Is power generating? No, it's utilization equipment is equipment that is being utilized, a load, a device, non-industrial machinery, washing machineries, air conditioners, appliances are utilization. Generators are not utilization equipment. Solar arrays not utilization equipment. AHJ stands for the local authority having jurisdiction. So remember, the AHJ is the one saying we're going to use National Electric Code. So they have final authority to override National Electric Code or change it or add to it. And usually when AHJs add requirements to an installation, that at the bare minimum, that means they have a department that's looking into the subject matter, and they might have a little more flexibility than code does. So if a issue does arise that needs attention, they can step in and implement it without having to wait for National Electric Code. So one of the main instances that I've come across is in like New York City row homes. They can require more robust conduit sizing. A conduit like intermediary conduit or rigid conduit instead of a more flexible EMT conduit, out of concern that, hey, these are buildings that could cause, a whole lot of fires, not just the one house, but everything else, all the houses down the row. So they require tall buildings. They might require better conduit protections. Bonding is what you would think of as grounding, when things are grounded together, but it's not touched the ground yet. So, the ground is really like the, you want your during a fault, you want to be able to control where that electricity goes. You want breakers to be able to open. You want loads to be able to disconnect. And if you just had everything connected directly to ground, there's certain instances when you want to do that, such as extending the ground from the building up to all the metal non-current carrying parts. But as far as the circuit itself, you wouldn't want the circuit to be grounded. And so you have a return path for that electricity to go into the load and then out of the load. And how that return path is bonded to ground creates the flow of electrons. But we don't want that flow of electrons just to occur anywhere in the household, such as it would during a fault. And so, we see the term bonding to denote when we're connecting, two pieces of metal together, and then eventually that might be connected to ground, or it might already be part of the ground, but it's not as specific as the word ground is. Continuous loads are loads that would be on for 3 hours or more. Non-continuous loads would be loads that would be on for less than 3 hours of like constant operation. And then another one is the term dead front, which is the name for, when you open up a service panel lid, but you can't see inside the panel. That shield between you and the breakers is a dead front, and so I've found that term is useful to know, because sometimes a disconnect switch may not have a dead front, and a local inspector will say, hey, I want to see this, with a dead front. Okay, so under the concept of continuous loads, which of these loads would be continuous and which would be non-continuous? Really, what's important here is solar a continuous load or a non-continuous load, because the sun is not up all day long. But a solar array is on for 3 hours a day or more. A solar array is a continuous load. A dishwasher is not on for 3 hours, straight, but an air conditioner and a refrigerator are. And so, out of all of these, I'd say the dishwasher is the non-continuous load, and the rest are continuous loads. I'm going to start picking up the pace a little bit. A branch circuit is what electricians call the circuits in your homes, but there's a certain kind of circuit called a feeder, which transfers, power from one distribution panel to another. So, many small homes just have one, service panel, and there's a feeder circuit going into that panel from the utility, and then branch circuits coming out of it. But on larger facilities, you might have a series of disconnect switches feeding a series of distribution panels, and that would be a feeder circuit. Now, what's interesting to me about this is an air conditioner on the side of a building is usually on a dedicated circuit. And so if you just wire the air conditioner directly up to that, then the circuit could be considered a branch circuit. But if you put a service panel on the outside of the building where the air conditioner is, that could be considered a feeder circuit. So solar arrays and batteries, they're not allowed to share branch circuits. You're not allowed to plug a solar array into the wall. You're not allowed to share the same circuit as non-related loads. But you are allowed to connect to feeder circuits. So, under the right design for a small solar project, it's perfectly acceptable to take that internal wire run that's already been made between the air conditioning unit and the service panel, and where the wires come out to feed the AC, that can be a point of a convenient point of interconnection for a solar array. Charge controllers are DC to DC devices rather than DC to AC devices. So, used to be quite common, but a charge controller charging, this is a DC device. Let's see. We have the difference between tubing and conduit. Basically a tube is something that's fully enclosed. So most conduits are tubes, if you had to really get down to it. The type of enclosure can be similarly specific. There's fences, full enclosures, enclosures that are just intended to prevent accidental contact, and then, enclosures that are, needing to be fully enclosed. And then fittings are the general term for all that balance of system electrician stuff. The little brown piece on the Tinker Toy set that everything plugs into or connects things together. And all of this stuff, the fittings, the bushings, those connector points, that can be the hardest part of the design, is to get those correct. Knowing how to specify that material can be incredibly valuable to project logistics. It can be the difference between very expensive turnkey contractor and savings resulting from dividing the scope up and doing a little bit more on the design end. Other important terms: the effective ground fault path is the path that the electricity is supposed to take if there's an electrical fault. That doesn't mean the electricity always takes that pathway, but if we're, the point of the equipment grounding system, when you see that ground in the side of your wall plug, the point of that ground is so that if there is a problem right at that outlet, that the electricity has a place to go and clear to ground. Otherwise, it might be going somewhere else, like, into your non-related metal devices and arcing further than it should and causing a fire. Let's see. Then we have a grounded conductor. This is the weird thing, if you don't have a solid understanding about electricity, is we think things in terms of being like on and off, but it's really more like, being on top of a mountain or being at the bottom of the mountain, having a lot of potential energy or not having any potential energy. And you need that difference in voltage potential for electricity to move. So we hear about, birds being able to sit on power lines because there's no voltage potential between them, so they don't electrocute themselves. Okay, but the way that we get electricity to work in our circuits is, the electrons need to flow from a high potential to a low potential. So the return path for electrical flow in AC wiring is the neutral. And the neutral wiring is intentionally connected to ground in order to create that voltage differential so the electrons can flow from the hot legs, to ground. Now that connection, that intentional grounding, is only made at one point, because we want a funnel. We don't want a sifter. We don't want the electrons just to flow out any direction. And in fact, there is a kind of a drain, would be an analogy. The final ground on a home needs to be a lot larger than the ground paths for the effective ground pathways for the individual devices. So all the effective ground paths do eventually stack up and get larger and larger the further you get towards your point of interconnection. We're going to talk about arc faults and ground faults and fault protection in just a minute. So we're going to kind of just leave the rest of this stuff for your reference. So let's talk about arc faults and ground faults. In the news, I guess as of last year maybe, Walmart sued Tesla to get out of all of their Solar City solar leases. And that could be a huge loss, if it went through, because a lot of these solar leases were crafted at a time when there were excessive solar subsidies. And so the lease value, and solar was more expensive a few years ago than it is today too. But a lot of the lease values, what made a really profitable project a few years ago was the combination of the subsidies and the declining costs. And to make a lot of money off the projects, Solar City would just take whatever they could, share the least amount of profit with the lessee because they want to keep the money. Well, if you cancel all the 22-cent a kilowatt hour solar leases and replace them with 5-cent a kilowatt hour solar leases, that would be a huge financial loss for Tesla. So I can understand why Walmart, looking at the value of solar leases today, they're saying, I want to get out of these. How do I do that? And all it takes is a couple fires breaking out for them to say, that's our, that's our outlet. Now, this case was later settled, but at the time, the Tesla was wanting to blame the manufacturer of this connector, and that was never that argument was never held up in court. What is much more likely is the installer can mess up this connector in a variety of ways. These MC4 connectors are the weak point on a solar project. If you take any electrical wire under load and you disconnect it, that electricity as that cable is being pulled apart is still going to try and jump across this air gap. And so when you get a fault between one cable to the next through the air, that's an arc fault. And arc faults don't need to occur just in an air gap. Any loose wire terminations where the nut or the bolt is not torqued to the manufacturer's spec can cause arc faults. Stranded wiring that is poorly secured onto a terminal can cause arc faults. And back in the day, inverters did not have arc fault detection in them. And so perhaps the reputation of solar inverters for being string inverters for being bulletproof was, to some regard, hiding some workmanship issues of installers because an arc fault can be occurring with the equipment still operating. If there's not much arcing, just some arcing, the rest of the electricity is still going through the circuit. If your inverter doesn't have arc fault detection, you could have a workmanship issue on the roof starting to catch a fire on your roof, and you wouldn't do anything about it. Now, as in other industries, but particularly true with electrical industry, it comes down to good workmanship, and particularly on commercial projects, you should have electricians do this work. But there's other aspects of solar that are not electrical work, and it's labor work. So generally, what I do is I get the most experienced worker to make up these MC4 connection points. So an arc fault jumps between two gaps. Just on some final detail, you got to make sure that crimp is right. You got to make sure that it's tightened up around. This connector is tightened up tight. And then you also have to do good cable management. You have to make sure that this connection right here doesn't drop down onto the roof deck, which could later become saturated with water after it rains. And so here's a solar project on a flat roof. And, it looked like a pretty good project. But what we discovered getting into it was that the roof was lower than the drains on the roof. Well, that's weird, but this is an old building, and the roof had been put on and taken off a couple of times. And for whatever reason, the drain pipes from these roofs were sticking up out of the rooftop. And in fact, I guess you can't really see it in these pictures, but there was a little, in order to seal the penetration for the drain pipes, they had to build up that section of the rooftop, and it resulted in a little levee surrounding the drain. And so every time it rains on this rooftop, the whole frickin' roof turns into a lake of water. Now, look, I think that putting a solar on top of a roof like that is not a good idea. Okay, but as the as the contractor, by the time we're discovering that, it is what it is. And so what you have to do is make darn sure that all of your cable management is keeping these cables nice and tightly wrapped around these module frames. What you can't have is these loose MC4 connectors sitting in a puddle, because if it's sitting in a puddle and water's getting in there, you could have for that has potential to be a ground fault issue. So if you have energized water and you step in it, is that going to be a ground fault or is that going to be an arc fault? So an arc fault is between two wires that are kind of pulled apart. A ground fault is when that electricity instead makes a connection to ground. And so if you have an MC4 connector in a puddle and it's on an insulated roof, and then you go and you step on it, hey, maybe nothing will happen. But if that puddle goes up to, the metal on a piece of equipment on the rooftop and that metal's connected to ground, then you would have a ground fault. And maybe that ground fault is actually what you want. Is a ground fault a bad thing? Well, it can be. It can also be an indicator of a larger problem. Well, what we have to do is better understand the limits of these systems for detecting ground faults and arc faults. But being able to diagnose the difference between a ground fault and an arc fault can help you figure out what the cause of it is. And so here we have two wires that are landed on a terminal block, and we want to figure out what's gone on with this issue. And so what we have here is this is the AC terminal block. So this is going from the grid into the block. So the question is this an arc fault or is it a ground fault? And here's the neutral conductor. And that looks all right. What we have is leg 1 and leg 2 of power. This is the two. You don't have a positive and a negative coming in from the grid. You have a leg 1 and a leg 2 of equal but opposite 120 volt AC sine waves. And that makes a 240 volt potential across them. And what happened here is to me, it looks like we got some arcing between the leg 1 and leg 2 conductors. And so one thing that I think do-it-yourselfers should take under advisement is that these terminal blocks for these power inputs are right next to each other. There's not that much space between them. So if you get things wrong, like stripping too much wire off of the end of the cable, on an AC breaker panel, things are a little bit further spaced out than in a solar equipment, and solar equipment is quite expensive. And so what this was basically a $3,000 piece of equipment that was bricked, because the manufacturers are not compartmentalizing their control boards and letting you take a control board and put a new one in. They swap out the entire unit. And that arc fault was caused by stripping too much cable off of the conductor and it arcing because it's right next to this other conductor. So, poor workmanship. And I'd say that is what most problems are on a solar array, is poor workmanship. So take that in mind when you're selecting an installation contractor or considering it do it yourself. These manufacturers specify exactly how much, and it can be a different amount at different terminal ports on the inverter. So that's all stuff that you find in the installation manual, but you have to follow it, or at least make sure that whoever's stripping the cables is looking up the terminal links and getting them right. Let's talk about system grounding. We're going to take a break at the hour-and-a-half mark, so we still have a ways to go. Aren't you lucky? This ground wire, this green ground wire here, that is our effective ground fault path. If something goes wrong, if a meteor rips a hole through the panel in the microinverter, and now it's just empty space and silicon, and the sun's up and there's no clouds in the sky, and so things are just, it's a really bad day. Probably have to deal with a meteor, but that lands in the swimming pool, and now we have the solar array to take care of. What the goal of the effective ground fault path is to take that electricity and shuttle it into ground. Normally, that electricity would be flowing through the neutral back to the service panel. And then there's one point, and it can be inside the meter or it can be at the service panel. Well, there's one point where this neutral wire is connected to ground, and that gives the electrons the ability to flow. And of course, your ground has to be actually grounded too. There's this other part of the ground system, which I've been calling the drain, which is really called not the equipment ground conductor, which is the effective ground fault path is the equipment ground conductor. This green ground fault path is sized for this equipment, for this circuit, going back to the service panel. And then based on the total size of the service, the drain is sized and makes that connection to ground. So we got the equipment ground conductor that then feeds the grounding electrode. We're going to talk about that in a minute. A ground rod, a ground plate, a whole bunch of copper wire thrown into the ground. Whatever is your grounding electrode technique, there's a few of them. There's a special term for the very last ground in the stop, which is the grounding electrode conductor. And I don't know, sometimes that needs to be a little bit, 400 amp services needs to be a little bit larger than a 200 amp service. So keep that in mind. So how does a breaker work? When there is a ground fault, how does a breaker know that and interrupt that? Well, there's a couple of different, not all breakers have ground fault detection built into them. That GFCI breaker is the one with the little push button on it. Not all the breakers on your service panel have that. So what do regular breakers protect? Regular breakers are your overcurrent protection. If this is a 40 amp breaker and you got 40 amps going in and 40 amps coming out, and this is a 40 amp rated breaker, once this breaker goes up to 41 amps, this breaker should trip. So how does it do that actually? Well, it basically uses the heat from the wire to physically, this coil moves, expands and contracts with heat, and that expansion drives a lever that literally opens up the switch. So it's heat driven based on having too much current flowing through that conductor. So it's just an overcurrent protection device. And so we have breakers to make sure that if our devices are malfunctioning in a way that they're pulling so much power through that it would cause the cables themselves to start burning up, then the breaker trips. If I'm taking a device that is malfunctioning, and normally it should be drawing some power, but for whatever reason it's drawing twice as much power, the breaker will trip too. If you take a device that is leaking a little bit of power but not all of its power, a regular breaker won't have the heat necessary to open up and pull it apart. And so what a GFCI breaker does is it inserts a computer chip into the board, which is very ironic because National Electric Code really likes manual switches as a matter of principle, whereas European codes, you're less likely to get this aspect of the breaker because they say this aspect of the breaker is good enough. And so European service panels are cheaper and smaller and in many ways more tidy. American products are bulkier, more expensive, but they also have the added benefit of this, mechanical switch. But back on the GFCI breaker part, just like an electrician has a clamp meter where they can clamp around a wire and monitor the current flowing through it, the breaker is monitoring the current flowing through the return of the circuit. And if it notices a fluctuation in the return that is less than 40 amps or 20 amps, it might only be 0.1 amp or 0.2 amp, depending on how sensitive the device is, it can trip the ground fault and turn off. So where it's using, circuitry, computer chips, computer boards, science, not just brute heat to detect lower amperage ground faults. So I think the important thing to keep in mind is just a regular breaker by itself is only for overcurrent. It's not for instances where it's undercurrent. It's not for arc faults. And for that reason, the inverters today are listed for arc fault detection and ground fault detection. They didn't have those features when they were first starting out. So by and large, you want to assume that a breaker trips for a reason. If I have a customer call me and they say, well, the breaker tripped on the solar array, I don't want them to reset the breaker and just see if the system starts up again. A better process would be to give the system a visual inspection to see if a fault occurred because of something not going off. But in this case, the inverter didn't flag an error when just a little tiny arc connected the two together, and the breaker only tripped when you got enough current flowing. So anyway, the problem occurred without flagging without really flagging the issue. I don't know if I said that right, but the breakers don't trip for no reason. It's very rare to have a breaker that's tripping because it's at the end of its life and the coils are expanding at 35 amps instead of 40, and so it's tripping when it's not supposed to be, as an analog breaker would. But also, not all breakers can detect all kinds of faults and prevent all kinds of faults. All right, so picture is worthwhile. You know what, we can see the heat from the cable. Amperage is a heat issue. Voltage is more of an explosive issue. And what we're seeing here is signs of melting rather than pulverization. This is an amperage issue. And arc faults can naturally occur when you have an energized load and you flip that breaker and you have a disconnect. You'll have an arc fault. Arc faults can precede ground faults. So if you drive a nail into live electrical wire, it may just arc fault, and that might be I would hesitate to say it's less of a safety issue, because the heat from that arc fault can cause a fire. Also, the power quality from the circuit to the device can cause the device to fail. But generally, you'll have arc faulting that then finds a path to ground and becomes a ground fault. The neutral load calculation. So sometimes the neutral can be undersized. And the answer is, well, why, when you're using a neutral, why can it be undersized? And the two answers would be, we've actually covered already. The first would be if you don't need it. The neutral's just there as a communication circuit. You may be able to undersize the neutral. Generally, in that specific case, what do you undersize it to? And the rule is you can undersize it to the size of the equipment ground conductor, so that it can't be smaller than the equipment ground, but you're effectively installing a secondary equipment ground conductor by having a useless neutral that's undersized. The second case where you can undersize your neutral is if you have loads on one sine wave, on phase one, and then you have an imbalanced load on phase two that's not drawing as much power, and the neutral. So if we reflected that, the question is, well, the neutral, which is balancing the true loads, it doesn't have to be sized to balance the entire load, as if this phase were completely on and the other phase was completely off. We have both phases being used by multiple pieces of equipment at the same time. If we can undersize the neutral under the assumption that the net difference between the two phases is not going to be at 100% of the value between the two phases. So often in this case, it says for kitchen equipment, you can undersize the neutral by 30%. That's kind of in the solar industry, you usually have the budget for a full-size neutral if you're going to use it, even if you can undersize. All right, so here where I guess we had defined nominal voltages, but I think it's useful to look at what's going on here. This is the point of interconnection being made. After this, we'll take a break. But what we have in this picture are utility feeder conductors. This is from the solar array service panel, and they're hanging a transformer off the grid, and they're going to wire that transformer into these conductors. And so the grid side is at 2.4 kilovolts, 2,400 volts, and coming out of the transformer on the other end is two 120 volt legs, plus a neutral. And that neutral's purpose is to balance the load difference if there's more load on one leg versus the other. So how do we get from 2,400 volts to 120 volts? Well, the symbol for the transformer is indicating the actual copper windings that allow the electricity to be transformed from high voltage to low voltage. This is actually a cheaper and easier process to do with AC electricity rather than DC electricity, which has to be more like computer controlled rather than naturally controlled. And so actually DC has a lot of merit for being the standard electricity, but the reason why AC won out is how much easier it is to transform so that we can do things like step it up to really high voltage so that we can transport that electricity over longer distances.